We have our new unit. This unit is on linear systems, and we're going to learn what that means. And I think the best way to learn what something means is to kind of maybe look at an example of it. So this part's not in your notes, so we're just going to kind of talk about this a little bit. How many people in here actually have a cell phone? That's a lot of people. Wow. I used to ask this question, and like maybe I'd get one or two people would raise their hand, and we have almost everybody. That's amazing. So as you may or may not know, cell phones are pretty expensive, aren't they? I don't know, maybe you don't know this. They are. They're pretty expensive. So I have a problem here where I'm trying to figure out what cell phone plan I should get, because there's so many different ones. Now I greatly simplified this problem, because if this was really what goes on, I don't know if you've ever been to like, AT&T, and you go to Sprint, and you go to T-Mobile, and like they'll have just so many crazy different plans it's impossible to figure out. So I simplified it a little bit. Let's say these are two companies, and we found this is what they charge. So company K, what I'm calling them, they charge you $5 a month for your cell phone, but then if you use it, 50 cents a minute. Okay? So $5 a month, every month you got to pay $5 no matter what, and then when you use your phone, they charge you 50 cents a minute. Company L, now they're charging you more a month. They're charging you $10 a month, so that's more. So first you're like, I don't know, do I want that one? However, they're only 25 cents a minute. So they're charging you less per minute. And now you got to figure out, well, which one should I use? When would it make more economic sense to use one versus the other? Like, how do you make a decision like this? How do you do it? So if you spend a lot of time on your phone, you're a big talker, you say company L. Now tell me why you said that. Okay, so, yeah, do you want to add something?
If you don't go, like, on your phone a lot, you don't want company L because it's charging you $10 a month whether you use your phone a lot or not. And so if you don't use a lot, you probably less
Up front. Okay, I think you guys are trying to say the same thing. So the factor here is how much you use your phone, how much you talk on the phone. So if you don't talk very much, Brandon says choose company K. And if you talk a lot, Baden says choose company L. What do you think?
Yeah.
All right, so then my question is, well, so how do I know if I talk a little or a lot? Like, what's that magic number that says I talk a little or... Don't laugh. Okay, I talk a lot. I know that. But who says I talk a lot on the phone? Right? So I need to know that. If I knew that magic number, and I could figure out, oh, I definitely talk more or less than that magic number, then that would be, a way I can choose. Yeah. Well, what's the magic number?
The number of minutes that you use your phone in a month.
Yeah, I know, but what is that number? That's what I need to know. That's what I'm trying to figure out. If I knew that, Ryan, you're right. If I knew that, then this might be an easier thing to do. So what we're learning with linear systems is a way to figure out that magic number. So that I know, where is it, where I go for company K, and where is it that I go for company L. So that's what we're trying to figure out here. And my board showed up, so it's coming back down. All right, so let's see how we do this, how we can think about it. So I'm going to make a little graph here, but I have to think about how this stuff works. So here's my parameters here. Company K, $5 a month at 50 cents a minute. Company L, $10 a month at 25 cents a minute. So can we write equations to describe the plan? So I'm going to let let's let y equal the cost. And I'm going to let x equal hours that I talk on the phone. Okay? Hours or minutes? Minutes. I'm talking about minutes. Because they charge by minutes. So let's think about this. $5 a month and 50 cents a minute. So let's say cost per month. How about that? So per month, how many $5 do I have to pay? 5 of them? One, right? One $5 payment. So my cost, my y, is $5, right? Plus what? How much I talk per minute, right? So x X is the number of minutes I talk. Well, let's say I talked 1 minute. I would just add 50 cents to this, right? If I talked 2 minutes, what would I be adding in here? $1. If I talked 3 minutes, so what are you doing? You're taking that number of minutes and you're multiplying it by 50 cents, right? Well, I'm multiplying it. Think about what would it be for 4 minutes? $2. So it's 50 cents times 4. So you take that 0.50, and I'm just going to make it a 0.5, and you make that an X. Because X is the number of minutes, right? So if it's 1 minute, $5.50. If it's 2 minutes, that's $1 plus the 5 you already spent. 3 minutes, $1.50 plus the 5. Does that make sense?
Yes.
Okay. Now that's company K. Oops. Bring it up here. Technology. Okay. So that's company K. What about company L now? Kind of using the same idea. Y is still cost per month, and X is still minutes. So Matthew, what would that be? What do you guys think, right? You're paying that $10 payment one time, and then 25 cents for every minute that you use. Excellent. Okay, so now we're making this into math, right? Turning this problem into a math problem. Now to graph these equations, I think what I'll do is I'm going to turn it around a little bit so that it looks like y equals mx plus b. We're not allowed to do that. Commutative property, right? Commutative property of addition says you can change the order when you're adding stuff. So I will. The other thing is I kind of prefer it to be in fractions. So I'll make that happen because I need slope. How do I graph if I don't know slope? So how about that? Going from decimal to fraction. You guys said that decimal's not important. Alrighty. Let me think now how to graph this. For the first one, m equals half, right? It's company K. And b equals 5. Alright. Well, oh boy. You know, here's a little sneaky thing I think that might help us. Is 1/2 the same as 5 tenths?
Yeah.
So you remember what I was saying, reduce, reduce, reduce? I'm actually going the other way now because I looked at this and it looked like that might be hard to graph on that, but I think I can do 5 tenths. So if b is 5, and this is going to be company, I'm going to make company K red. So b is 5. This says go up 5 and right 10. Oh, maybe I should make this another 20. Maybe that's even better. I don't know. We'll see. So if it's 10 over 20. Oh no, I'm sorry. No, I'm back.
It's 5.
5 are better. So I'm going to go up 5, right 10. Up 5, right 10. Up 5, right 10. Up 5, right 10. Yeah? There it goes. This is company K. Now, why am I not going this way? Because, you know, typically the line goes that way. Why wouldn't I do that, Gigi?
Because that one is inside, that there's more points, there's more minutes on the graph.
Well, then they're over here. What is my domain over here, right? This would be negative minutes. Now, unless you're like, you know, going backwards in time or something, I don't know. I gotta, somebody in my last class, well, if you're a time lord, no, we're not. I don't care about starting here, but no, we're not. So we're just talking positive minutes now. So that's company K. So let's now look at company L. So that one, the minutes are 1/4, and the B is 10. Once again, I think I want to change that 1/4 into something more manageable for this. What might I want to change it to? What do you think? 5/20. That's a good idea. Because I'm just looking at what this is, and what other color can I use here? Pink. So this one says your B is 10, so you're starting from here, right? It costs more. So at first. So I started 10. That's not a big difference. There we go. Can you see that, guy? You guys see that? So now I'm going to go up 5, right 20. Up 5, right 20. Up 5, right 20. And this is company L. Well, I don't know. Is company L better? Now, I don't know. At how many minutes is that break-even point, that magic number we were looking for? Where is that thing, Ryan? 20 20 minutes, I kind of missed, but right here, right, oops, this point, it's on both graphs, isn't it? So 20 minutes will cost you $15 with company K, and 20 minutes will cost you $15 with company L. So if you are somehow, you know every month, you speak exactly, no more, no less, than 20 minutes, which plan should you buy? Doesn't matter, right? So at 20 minutes, exactly the same. Now, if you are a person who has your phone just, and anybody have a cell phone, your parents are like, this is just for emergencies. You call me, you know, the limb has fallen off, you know, that's when you call me. So you got one like that, right? You not, no? And nobody has that?
Some tells.
Really? You guys just
I
been
don't have a
talking?
cell phone.
Yeah, just.
Okay, you don't have one, right? So well, okay.
Only do my phone.
You're going to kind more emergencies, right?
Kinda like that.
You're not supposed to. So, if you're that person, which plan makes more sense to you? I'll ask you. Wait, you don't talk a lot on it, so which plan might make more sense if you like to save money? Company K, right? So if you're speaking less than, we're not doing text, we're just talking on the phone here. If you're speaking less than 20 minutes, then it makes more sense to take the one that costs less. That's company K. Now, if you are a chatty Cathy, yeah? So chatty Cathy is that was like one of the first talking dolls, right? Chatty Cathy. What did you say? That's your mom?
Yeah.
Oh, that's cool. Really? Well, what plan? If you're talking 56 minutes in just one call, wow. What plan makes more sense then? L. Okay? So this is the beauty of these linear systems. I kind of can look at graphs of both, figure out kind of the break-even point, and then make decisions based on data. So this is why we do it. So I want you to keep this example in your mind the whole time, because what's going to happen is it becomes like everything else in math. Oh, you do this, you do that, subtract this, add this, you know, whatever. And then we forget the whole point. Why are we doing this? Because there actually is a real application for stuff like this. Anybody have like GPS in their car, on maybe on their phone, GPS? Everywhere, right? Do you know what it is, GPS? You don't have it?
Yeah.
It's a global positioning system. It tells you, it can tell you where you are on Earth, right? And it was developed by the military, but now we found all these nice applications for it. And GPS uses linear systems. That's how it kind of figures out where you are. So it actually has, I think, 3 instead of just 2. You can have more too. And so, because we live in a 3-dimensional world, it has 3 different places it finds you. So linear systems have a lot of real-life applications. So I want you to keep that in mind. As we're kind of going through this, as you're saying, oh, it's just another math thing, it really does have some applications. Remember why we're going through this. Okay, so yay. Let's see what we know about or can learn about them. So a linear system, what is it? That's always important to know. It consists of 2 or more, you can have more than 2, linear equations in the same variables. So notice when we did the example with the cell phone, x always meant the number of minutes, and y always meant the cost. They mean the exact same thing. We're using them the exact same way in both of the equations that we're using. A solution to a linear system, this is important, is the ordered pair that satisfies each equation in the system. What does that mean? Go back to our picture here. This is a solution to this linear system. It is a point that's on this line, and it's a point that's on that line. This XY pair, 2015, if you were to plug it into this equation, you get a true statement. And if you plug it into this statement, into this equation, you get a true statement. Because remember what these are. This equation describes this line. Every point on this line, if you plug in the x and the y, you get a true statement. Same thing with this line. Every XY pair on this line, you plug it in, you get true. Now, if I were to plug in a point not on the line, do I get a true statement? No. So the idea is a solution, when you plug it into both equations, you're going to get a true statement because the point is on both the lines. That's a solution to a linear system. The point of intersection of the two lines, where they cross, that's the solution. That's important. Very important thing. It sounds kind of okay, but some people kind of miss that. It's the place where they both cross. Point is on both lines. So here's an example that I've got here of a linear system. I've got two equations in two variables, x, y, x, y. They are the same variables. They mean the same thing. This one is 2x plus 3y equals 6. This one is negative 2x plus 4y equals 8. First of all, are these linear equations? How do we know if they are linear equations or not? Okay, well, yeah? What do you think, Matthew? But let's think about linear equations. Remember this one? If something is in this form, it's a line, right? Y equals mx plus b. Remember this form? You don't?
Oh, yeah, I do.
This is standard form. This is slope-intercept form. Anything in this form is a line. Which form are these equations? Are they slope-intercept or standard? Standard. Ax plus by equals c. Because they fit this pattern, these are both lines. So these are linear systems. There are systems that aren't necessarily linear. This one is. Now, how do I know if something's a solution? This 2, 3. If it makes both these equations true, it means this point is on both lines. So if you were to graph them, they would overlap it this way. So how do you test? I don't know. Let's plug it in. Let's see. Is 2, 3 a solution to this?
No.
No? Well, wow, you do that in half. Let's try it out. Right? This is x. This is y. So 2 times x, which is 2, plus 3 times y, which is 3. You're asking a question. Does that equal 6?
No.
Well, I don't know. This is how you show if it's a solution or not. Everybody looking? Like if I were to ask you on a test, is this a solution? You would actually do the math. If you leave me math to do, you haven't done your job. I want a number compared to a number, and no, it's not.
That's 13.
Third, sorry. But it's still not 6. I'll tell you that. Not 6. So this one is not a solution because I already found one where it doesn't work. It has to work in both. Let's try 0, 2 and see if it is a solution. So this one was 2, 3. Let's try 0, 2. Now, you guys, I just did it in my head. It's so much faster. You really have to show your work. You're writing me a math essay. You're explaining your brain to me when you do this. So that is why we're doing it, because if I don't know what your brain's doing, I may not give you any credit for it or understand that you did it. Okay, so I plug in the x, I plug in the y into 2x plus 3y equals 6. Evaluate. What did I do? 0, 2. That's a 2. That's it.
Wait, 3 times 2.
It's a 2. That was me writing the wrong thing. It's 0, 2. So it works in this one. Yay! Does that mean it's a solution to the linear system?
No.
Not necessarily. It has to work in both. So now you say, well, let me test negative 2x plus 4y equals 8. Negative 2x, which I think is 0, plus 4y, y is 2. Does that equal 8?
Yes.
0. You have to go number to number if you're going to say yes. Did everybody hear that?
Yes.
This is what it looks like to show something is a solution. I checked in the first equation. I checked in the second. It works in both. Yes, this one is the place. If you were to graph these two lines, you know where they'd intersect? At 0, 2. Just like you know in our warm-up, you have those places they're intersecting. Just like with our phone plan. Everybody with me? Everybody's looking up there like rapt attention. Good. All righty. So, how do we find these solutions? Solutions occur where lines intersect. So I actually graphed those two. 2x plus 3y equals 6, and negative 2x plus 4y equals 8, and they do indeed meet up over here at 0, 2. So what we did over there was find this, okay? That's a solution. So if I ask you, is this a solution to the system? Plug them in both. If you get true statements both times, the answer is yes. Otherwise, no. Okay, so one way to find solutions is to graph them. Graph them. Find a place where they cross. So we're going to look at the first method. We're actually going to learn 3 different ways to find solutions to linear systems. I think you meant, yay, pretty sure. And this method 1, graphing. So how does it work? You graph both equations on the same little plane. You say, it looks like the point of the intersection is right there. I think it's there. And then you verify that. How do you verify? You take that point of intersection, plug it back in both equations, and make sure that it makes both equations true. Get it? Let's find out. So here's an example that's on your paper here. So we're going to find the solution to this linear system. So step 1 says graph both lines. So let's see, if I want to graph 3x minus y equals 2, what method should we use? Remember, we got several different ways to graph a line.
Why you doing something?
I like that one too. I think that one's the easiest. So what's the problem though with this? And what's the slope? What do I have to do, Matthew? I have to put it in y equal mx plus b form. So he's saying subtract that 3x and get it to the other side of the equal. So I'm getting negative y equals, I'm going to put this one first because I want it to be in mx plus b form. And this gives me negative y. I don't want negative y. So what do I do, Red? Divide negative 1 or multiply. And remember what that does if you multiply both sides by negative 1. First of all, what gets multiplied? Everything. So negative becomes positive. Negative becomes positive. Positive becomes negative. So now we're in y equals mx plus b. What's m? And what's b? B. So I graph my b. This is really 3 over 1, up 3, right 1. 1, 2, 3, right 1. 1, 2, 3, right 1. 1, 2, 3. Does it look like we're going to have a nice positive slope here on this line I'm graphing? That's good, right? Because this is a positive number. I'm going to go down 3, left 1, down 3, left 1. Okay. And now I can draw my line here. It's hard for me with my little play here, but I'm doing my best. That's that one. Now I have to graph the other one. Now again, this one, not in slope-intercept form. How do I get it there? Right, subtract this guy to get it over there. Y equals mx plus b. Okay, we're good. Now I need to figure out what the slope and the y-intercept are. What's the slope? Negative 1. Y-intercept. Alright, so let's go to negative 6. 1, 2, 3, 4, 5, 6, right? Negative 1. Put it over 1. Down and right. Okay. Down and right. Down and right. Am I getting a negative line forming here? Good, right, because it's a negative slope. Instead of down and right, I want to go up and left. That's equivalent. I can see my line now, right? I just like to fill my graph, and then I can, oops, connect that. And, what's my solution? What's my solution? Because number 2 says, what's that point of intersection? What does it look like? Negative 1, 1, 2, 3. It does kind of look like that. Why am I saying estimated? I don't know, maybe I make it, I can't really tell what it is. To me it looks like negative 1, negative 5. Now you do need to always verify that solution. Don't just say, okay, I found it, done. Put them back in. So here's the verification step. 3x minus y equals 2. I think x is negative 1, and I think y is negative 5. So let me plug it into that first equation. And look, be careful with all these negatives. I always put my x in parentheses and my y so that I don't mess up my negative. 3 times negative 1 is negative 3. But what about a negative 5 or minus negative 5? What's that? Plus. Now, I don't care if you see it already. Add those 2 together, you get 2. Let's look at our right side. Does it match? Yes. Okay, worked in this one. Don't stop here. You have to check the other one. X plus y is that negative 6. So x is negative 1, and y is negative 5. Do we get -6? Let me add them, or 2. Okay, now, since it works in both, every confidence, I got the right solution. So, if you skip this step, you don't know if you've done it correctly. And you turn in your test and you get it wrong. Should you ever get this wrong, you know ahead of time. Plug it in. Take a look. Simple, right? That's it. That's the graphing method. That's all you have to do. It's easy. Look at this. Verify solution. We did it already, right? But again, it's worth emphasizing. Do it in both equations. That's a common mistake is either you don't do it at all, or you just do it in one and stop. It can work in one and not the other. Certainly can. All right. Another example. I don't think I have this one on your page, but just to review one, so you can look up. Okay, so -x plus y equals -7. I have to graph that. Then I add x to both sides. What's my slope? Adding x. Adding x. It's always going to be the opposite sign when you do it. B equals -7. So okay. 1, 2, 3, 4, 5, 6, 7. Up one, right one, right? Because my slope is 1. And then down one, right? Good thing we're expert at graphing, right?
Yeah.
We'll pretend that warm-up never happened. X plus 4y equals -8. Subtract this x. 4y equals -x minus 8. Right? Stop me if I'm making a mistake here. I don't get y by itself.
Divide everything off.
Everything, I heard it. Everything. So this becomes y. I'm going to put my little 1 back in. I can see now that -1/4 x. Negative over positive is negative. 8 over 4 is 2. I think that's right. So I go to -2. And my slope is -1/4. So down and right. Okay. Down 1, right 4. 1, 2, 3, 4. See what's happening here? Down 1, 1, 2, 3, 4. Do I see my point of intersection already? And what point is it? What? I found it. So where is it? You're right, I should have extended it, but I'm not. 1, 2, 3, 4. Yes, you do. 4. 1, 2, -3. That's what it looks like. So am I done? Am I done? Yeah, I found it. Done.
No, you gotta check your work.
Check it, check it. Plug 4 and -3 into that. Negative, let's see, x plus y equals -7. Is that true? It's -4 plus -3. Okay, number compared to number. Works in this one. Let's try that guy. X plus 4y, so, x plus 4y, so 4 plus 4y equals -8. Let me see if that's true. That would be 4. A plus times a negative is a negative. Does that equal -8? Plus 4 minus 12? -8. So it works. Woohoo. Now I'm yes. With confidence. Yes, that works. That's the graphing method. Easy. Now there's a bunch on here. I'm going to just have you do C. Just do C. We'll see how that goes. All right, let's see how we did. So you made this into, hopefully you got y equals x minus 5. Who got y equals x minus 5 for this guy? Just 2 people? Wait, a few people? Right? You subtracted the x, and then you multiplied through by -1. So m is 1, b is -5. 1, 2, 3, 4, 5. Up one, right one, up one, right one, up one, right one. There it is. Is that right?
Yes.
And now this one became y equals -3x plus 3. Negative. So m is -3, and b is positive 3. 1, 2, 3. Put that over 1, down and right. 1, 2, 3, down, 1 right. 1, 2, 3, down, 1 right. Ooh, it's always nice when I hit somewhere, right? 1, 2, it stops. So let's see here, something like this. Here's where I think the solution is. So I'm going to write down what that point is. 1, 2. And then 1, 2, 3, -3. So how do I know that that's right? Who got this?
I got it.
So that means it's right by democracy?
I
You
saw
know
it.
people got it.
Verify.
Verify it. So you plug them in. So 2, that's x, minus the y, that's negative 3. Notice how careful I'm being. Minus negative 3 equals 5. 2 minus minus, what's the plus? So 5 equals 5. Awesome. So this one works. Now let's try this one. 3 times 2 plus the y, which I think is negative 3. I hope that turns out to be 3. Let's see what happens. 6 plus times a negative is a negative. I think it's going to work. 6 minus, oh, this is such a mess. I'm sorry about that. 3 equals 3. It's there.
Yes.
Yeah. So with confidence now, this is the place. This is the point that's on this line and it's on that line. Point of intersection. And remember, this is not, it's not only just an exercise. These can be used in real life. Alrighty. I'm going to move on. We're going to keep that away. The number of solutions. So on the back here, I just have a little bit for you to write. Oh, some noise here. Are we okay? Yeah? Okay. So sometimes we have how many solutions? Now, if the lines intersect once, how many possible solutions can I get?
Uno.
Yeah, how many called? 1, right? That's it. If they're lines and they intersect, they can only intersect in one place. Now, what about you graph the 2 lines and they become parallel?
Zero.
Do parallel lines ever intersect?
No.
So is there a point that's on both of those lines? No. So sometimes you don't have any, and sometimes you're going to graph those lines, and then the second line goes here. So where do they intersect? Everywhere, right? They intersect everywhere. So sometimes we have infinite number of solutions. Sometimes we do. You would write infinite. You would write that word.
You wrote the infinite sign?
No, write that word. Okay, so how do you know whether you do or not? So let's say I'm looking at this guy. Excuse me. All right? So to find them graphically, you would graph them, right? Well, that's no good. I have to subtract that 2x, right? And I have to subtract that 2x. Now I can go ahead and graph, right? Except, wait a second. What's the m here?
New 2.
Yeah, and what's the b?
New 2.
B.
Oh, new 1.
Now for this one,
New.
negative 2. I have the same slope, but different y-intercepts. These are parallel lines. How many solutions do I have? 0. And you can graph them if you want. Right? Can't hurt. But when I do, I expect to get my parallel lines. So I'll just put negative 1. Yes? You can say no solutions. Let's see about this one now. I have to put this in variable form, right? So I'm going to subtract that x, divide through by 3, right? 6 over 3 is 2. Let me move on this one now. That becomes 6y equals negative 2x plus 12. I need to divide by 6. That's negative 2 over 6. Negative 1/3 x. So the slope here, negative 1/3, and b is 2. Slope here, negative 1/3, b is 2. What's going on here? They're equivalent. I graph this, I'm getting the same line. So b equals 2, down 1, I'm getting the same line. So this one had no solutions, and this one has infinitely many solutions. Every point on that line is a solution. So that can happen. That can happen. Okay, so there are no solutions when lines are parallel. So I know this isn't on here, but you might want to just write this statement down. There are no solutions when lines are parallel, and there are infinite solutions when lines are the same. So just take a moment. Write those 2 statements down. You guys can't be writing it down if you're doing whatever it is you're doing over there. Write those 2 statements down. No. So far, what do we know? Linear systems are two or more linear equations in the same variables. Solutions to linear systems are the coordinates of the intersection, if there is one, of the lines in the system. It's where the two lines meet. That point is on both lines. To solve by graphing, graph both equations on the same plane, find that little point of intersection, and then verify that that point works in both equations, right? That's where we've been. Easy peasy. There's a problem though. Before we even go to this slide here, what would happen, like, if you were graphing it, I'm just going to make up one. We graphed two lines, and so maybe this was one of the lines. And then here comes the other one. Here's the point of intersection, say. What's the coordinate?
1, 1.
No.
Negative 1, 1.
Well, negative 1, 1's up
No,
here.
negative 1.2.
Negative 1 point something or other, right? And maybe this is point something or other. I don't know what it is. So I can make a guess and say, well, maybe it's negative 1.2, and maybe it's 0.8. Maybe. And what am I going to do? Try every possibility? How many different values can I guess between the negative 1 and negative 2? How many different possible x's are there?
Infinite.
An infinite number, right? So what is a problem with the graphing method? What's wrong with it?
It's not an exact decimal.
You may not be able to get the exact number. If it's not integer xy's, which believe me, most of the time it's not in real life. It's not. You can figure it out this way. What's good about the graphing method? It's easy, very understandable, right? Ooh, it's right there. Oh, is it fast? Maybe. If you're a great grapher, it's fast. If you're not a good grapher, it's bad, right? So the problem is with graphing, the graphing method, I love it because how visual it is, but it sometimes doesn't help us if it's not a nice little number here. So we have to have some algebraic methods. And we're going to learn one of these algebraic methods today, and that's called the substitution method. Yes?
Can you tell if the if you hadn't graphed it yet, can you just tell if you can't graph it?
I don't know. I can't. Some people have that kind of mind that in their brain they look at this, they see the graph, they know. I don't have that kind of mind. Do you have that kind of mind where you can just look and see the graph? Like I have an idea of what they look like, but I can't see that point where they're meeting. I'm not that good.
I mean, so if it's like a point, like 8 or something, you don't.
I think you don't necessarily know in advance.
Oh, okay.
Maybe. But I think, generally speaking, I think it's hard to know in advance. So we're learning some of these algebraic methods. Substitution is a nice little method. So you remember this. Okay. Step 1. What you want to do is, you know how there's two equations? One of the equations either has to look like y equals or x equals. One of those equations has to look like that. So I already have that here. That's good. Now if it didn't, I would solve one of them for y or solve one for x if it didn't. Okay, step 2 says substitute the expression in one of the equations, that's the y equal or the x equal equation, into the one that isn't like that. Substitute it into the other one, you'll see. And then you're going to solve for a variable. Then you're going to substitute back. What? And then at least we know how to do this. Verify the solution. So if you do 1, 2, 3, which I'll show you in a minute, the verification step is the same. You'll come up with an xy pair, plug it in here, you know if it's correct. So let me show you how you do that. And I can't remember if it's on the next slide or not, so let me just take a read. Yes, okay, good. So what you do is you say this one is y equals, right? That's step 1. Okay, I did that. Now it says, look at this, y and 3x plus 2. What does equal mean? What does equal mean? Same. So y and 3x plus 2 are the same. Who's got a great nickname in here? You guys have somebody with a nickname?
I have a good nickname.
I have a good one.
I'm Bob.
Yeah.
My squad.
Okay, I was looking more for Samuel and Sam. But what is it?
What? No, I said Sam.
Oh, I thought you said what? Okay, right. We have Sam and Samuel. We have Daniel and Danny, right? If I call you what? And Dan. If I'm talking about Daniel or I'm talking about Danny, am I talking about the same guy? Yeah. Am I talking about Sam or I'm talking about Samuel? Am I talking about the same guy? Yes.
Unless there's another Samuel in the class.
the same as 3x plus 2. So when I go down here, wherever I see y, you know what I'm going to put in instead? 3x plus 2. Because I'm going to substitute the same thing in there. So this second equation becomes this. It's still x plus 2y equals 11. I'm using y's other name, 3x plus 2. Yeah.
Oh.
Yeah, think about it. Think about what I just did here. Y equals 3x plus 2. If you're sleeping, look up right now because you will not know how to do this if you're paying no attention like a few of you are. So, same. So I'm going to replace it with its other name. Now, I don't know how to solve something with two variables, but I do know how to solve something in one variable. I can solve this equation. All I need to do is first distribute, right? Then I combine like terms. If you have an x and I add 6 more x's, how many x's do I have? 7 x's. Subtract that 4. X equals 1. Now what is that x? Remember what a solution is? It's an xy pair. I found the x value. Found it. So if you were to graph those two things, the place where it intersects, the x value is 1. Now I need to find the other thing. So what you do with that is you say, wait a second, I've got two equations here. And so I know one of them. Why don't I just plug that in and find the other? So y equals 3 times 1 plus 2. 3 plus 2 is 5. So what's y? 5. So it appears to be, if you were to graph these two lines, you know where they intersect? At 1, 5. I didn't have to graph it to find that. I solved it algebraically. Now how do I know I'm correct? Check it. So I know I just did this one. I always plug them back in just in case I made some kind of strange mistake. I fully expect this one to work, and it does, because that's how I found, the y value. But let's make sure it works here. So x plus 2y has to equal 11, right? X is 1 plus 2 times 5. Does that equal 11? And that's 1 plus 10. Oh! Woohoo! So we found the solution. We did not have to graph it. Does that make sense or not make sense? That's a little confusing here at first. You're like, wait, what did we do? So we got some new trays, but let me do another one because I think it's a little bit confusing at first. So let's look at A. All right, A. So I have an x equals. So remember, step 1 was to have an x equal or a y equal. I got an x equal. Great. Let's look at this next statement. X and 2y minus 6 are one and the same. So wherever I see an x, am I going to write x? No. What am I going to write? This. And make sure you group it. So here's an x. Instead of writing x, I'm going to use its other name in parentheses. Extremely important that you put it in parentheses. It's this whole thing times 4 plus 6y equals 4. 4x plus 6y equals 4. Who's with me on this step? This is the crucial step. Who's with me? Okay, with the question. But this is the most critical part here. Yeah, question? The x goes away. That's the beauty of it. Because I can't solve an equation with two variables. But I know x and 2y minus 6. This is Daniel and this is Danny. So instead of talking to Daniel now, I'm using Danny. What? Right? I'm using the other name for x. I'm replacing the x with 2y minus 6. 4x plus 6y equals 4. Yeah? And then we're going to just solve it. Distribute, because now I've got one variable. 8y minus 24 plus 6y equals 4. Well, let's see. 8y plus 6y. I've got 14y's now, right? Minus the 24 equals 4. Yes, sir? Yes? Yes, you do. You have to know how to do this. But you don't like it? Yeah, you do it a few times, you're going to get it. You will. All right, now what I just find here, your solution is an xy pair. The y value appears to be 2. Once I know that, I'm going to clear this up a little bit. Once I know that, I can plug the 2 into either one of these equations and find the x, right? So I'm going to do this one. It looks a little easier. So I'm going to say x is going to be 2 times y, which I think is 2, minus 6. Plugging it into here. 4 minus 6, that's a negative 2, isn't it? So I think that's the solution. That's the point. That if you were to graph those two things, that's where they meet up. Any possibility I might make a mistake doing all this algebra? You betcha. So let's check it.
Wait a minute.
What?
How do you do negative 24 get to 28?
I added 24 to both sides.
Oh.
Yeah. So let's see, plug that one in. That one should work. I'm pretty sure that one's going to work. X equals 2 times y minus 6. Is negative 2 the same as 4 minus 6? Sure is. Let's try this one now. 4 times negative 2 plus 6 times 2, does that equal 4? Now let's see, that's negative 8. That's a 12. Negative 8 plus 12, that's 4. Great. We found the solution. Okay? I would like you to try it. Now before you do, I just want to do a little bit of setup for you on question C. I'll just say, once you do C, you'll be able to do it. I lost my little mouse. Here it is. Notice step 1. Do I have an x equal or a y equal? So you look and you say, what looks easiest? To get it to an x equal or a y equal? First one, all I have to do is what, add y? And then I have x equals y plus 3. And now I know whenever I see an x, I'm going to put in a y plus 3 over here. So I want you to try these. This second one, y and 2x plus 5 are the same thing. So when I rewrite my second line here, 3x plus y. I don't want to write y, I want its other name. You with me?
Yeah.
Right? If you put it here, it doesn't make sense. X is x. Y is the thing that's something else. 5x plus 5 equals 10. Subtract the 5. X is 1. Building my point. Plug the 1 in. Y equals 2 times 1 plus 5. So y equals 2 plus 7. Verify. Did you verify if you got this? Verify, verify, verify. The only reason I'm not verifying right this minute is because I want to do 3. Or C, because I had a request for C. Okay, you guys, listen to this one. Because actually Claire made me think of a really important point, so I'm glad she brought this one up. So for this one, we're going to make x equals y plus 3. Now, would it work if we solved this for y? Yes. You can solve for either one. I don't care. You can solve this one for y. It's just going to be hard. I always look around what was easy, and that looked easiest to me. So if x and y plus 3 are the same, I'm not going to write x anymore. I'm going to write its other name. X is no longer x. I'm calling it y plus 3. Plus 2y equals negative 6. I could. But when there's no number in front of the x or just a 1, it just kind of comes out. Because it's distributing by 1, that is 1 plus y plus 3 plus 2y. But you know what? It's not a bad habit to always make it parentheses. Because I solved this one for x. I added y to both sides. X is y plus 3. Okay, solve this one for x. Add y to both sides. Yeah? Are you looking at me like, what language is this here?
I got it.
What?
I actually understand it now. I know.
But just, here, Amy, just solve this for x.
I got C, but I don't get C.
Look what you did. You have to solve for x. Add y to both sides.
Is it solved for y?
Because I need it by itself. If you'd rather solve for y, you can. X was easier. Plug that in. 1y plus 2 more y's. 3y plus 3 is negative 6. Shh, gentlemen. Subtract 3. Did we get y is negative 3?
Yeah.
That must be right.
Yeah.
We'll find out.
Now you did it.
Yes, ma'am. Well, what happened here, I'm replacing x with these. I solved it for y. Now, if you would have made this the y equals, you would be solving for the x first. Just stay with it. All right, so I think y is negative 3. Now, excellent point to bring up. Don't, so you know how I made x equals y minus, x equals y plus 3? Plug it back in the original, either this one or this one. I sure hope you're listening, because all I hear is talking. When you have rearranged things, when you look for the other variable, use the original. Has anybody ever made a mistake solving for a variable?
Nope, not yet.
Well, I have.
Oh, yeah,
I have. So I like to go back to the thing I know isn't a mistake. So x minus y, I think y is negative 3, would have to be 3. Negative, negative, so that's x plus 3 equals 3. Subtract 3, x is 0, I guess.
That's what I got.
So let's see, is it right?
Yeah.
How do you know it's right? Verify in both equations. Okay, for the last one. This one, I would probably solve this one for y. Subtract the 3x. Okay, finish this, right? Finish this. Take that y. It's going to become that.
In parentheses.
In parentheses, absolutely. And see if you can solve that equation. Did we get for part D, negative 2, negative 1?
Yes.
And you didn't need me to tell you that, right? Because you verified your solution and it was correct.